Okay, so let's start this session. This session, section 6.5, is about the singular value decomposition, or we said SVD in abbreviation. So in many applications, it's necessary to determine the rank of a matrix. So remember that. What is a rank of a matrix? That is the numbers of linearly independent column vectors in a matrix, right? This is called the rank. So the numbers of rank determines, you can say, determine the variation or the numbers of cases, not the numbers of cases, or the numbers of bases of the column space of the matrix. Okay, and usually we need to determine the rank of a matrix. And how can you determine the rank of a matrix? Theoretically, we can use Gaussian elimination, right? So given a matrix, you just work with Gaussian elimination, and then you can find the numbers of linearly independent columns, right? However, it's not practical. It's not practical in finite precision arithmetic, because in many matrices, because when we want to store this matrix in a computer, we need to digitize this matrix. And in many real applications, the numbers in a matrix would be of finite precision. Okay, and after a series of Gaussian illumination, many numbers in many values in the matrix would be very, very small. And because we don't have infinite numbers of precision, so if we work on many calculation, the numbers become very small, or it actually many numbers will not be equal to 0, but very close to 0. Okay, so in that case, it's unlikely that the echelon form will have the proper numbers of non-zero rows. Okay, because you may find you never get 0 rows, even if you calculate many times. Okay, and so it's more general or more practical to ask whether a matrix A is close to a rank deficient matrix. Okay, so we need a more practical way to determine a practical rank of the matrix. OK， 好，所以首先我先讲一下为什么我们要有 Section 6.5这一段。好，就在很多实际应用当中，我们常常去决定一个矩阵的 rank。好，那理论上这件事情很简单啊，我们就去做高斯消去法嘛。消完之后，那我们就看看说剩下多少个 non-zero rows， 那就是我的 rank 啊，对不对？好，理论上是这样，但是在实际的应用当中，你拿到的这些矩阵，你在那边消半天呢，其实最终几乎没有 zero， 没有这种zero rows， 就说你很难刚好把什么东西把一整列消掉，或者是说呢，有啦，你可能有消掉一些，但是你剩下来的 non-zero row， 你那个数字可能非常的小。比如说有一列，它的开头是 0.0000 几，好，那它是一个 non-zero row 啊，好，那但是呢，它是一个 non-zero row， 但是你也把它算成是一个 rank 的一部分，好，其实呢，这个并不足以非常准确的来描述这个矩阵的特性。那为什么会它就是没有办法消到0呢？或者是说它数字变得非常小呢？这有的时候呢，并不是因为高斯的错，不是因为高斯消去法的错， 而是因为我们在现实世界当中采集到的很多的数据都是有一些 noise 的，它有一些些微的 noise，所以你在那边消完呢，你你可能最后就是会差一点点，那个数字就差一点点，很接近零，但又不是零。OK， 所以在这样的情况底下呢，你可能就会高估了它的 rank。好，所以我们在这个 session 主要是要跟大家讲一个技巧，使得它更能够在实际的应用上，更能够让我们去理解这个矩阵的本质。好，那有的时候我们是，比如说这个 rank A，你如果用高斯消去法下去消，可能那 rank 是 n，可是事实上真正比较具有意义的 non-zero rows 可能是 m。好，那我要如何去评估它其实是它的本质是比较接近 rank 是 m 的一个矩阵呢？好，那这个就是我们这个章节要讲的事情。好，那所以一开始呢，因为等一下的数学会有一点麻烦，所以你好歹你要先知道说为什么我们要学这项东西。Okay, so we want to find a systematic way to ask whether a matrix is close to a rank division matrix. Okay, so for an m by n matrix, and assume m is larger than n. Okay, but in the following, the description in the following actually is not limited to m larger than n. Okay, the description is not limited to this case. This is just for simplify the description in the following. Okay, in fact, the following description satisfy also for m smaller than n. Okay, so for an m by n matrix A, the matrix A can be factored into a product U sigma V transpose. So here we introduce another decomposition, right? So originally we introduced LU decomposition, QR decomposition, right? And in the section 6.3, we also talk about diagonalization, right? So we can represent or we can decompose a matrix A by diagonalization. Okay, so here would be the fourth decomposition. The matrix A can be factored into a product U sigma V transpose, where U is an m by m orthogonal matrix, V is an n by n orthogonal matrix. Okay, and sigma is an n by n matrix whose off diagonal entries are all zeros. Therefore, the matrix sigma is a diagonal matrix. Right? So only the entries at the diagonal would be non-zero. Okay. And we assume the entries at the diagonal, the diagonal entries satisfy sigma 1 larger or equal to sigma 2 larger or equal to sigma 3 and so on. And then they are all larger or equal to 0. So the matrix sigma would be like sigma 1, sigma 2 to sigma n and so on. Okay? Okay, it's a diagonal matrix. Okay, so yeah, so the sigma would be looking like this. It is an m by n matrix. Okay, so here only the actually we cannot say it's a diagonal matrix. No, it's a n by n matrix where the off diagonal are all 0. So here are 0, here are all 0. Okay, so we have sigma 1 to sigma n, which may be larger or equal to 0. Okay, And the sigma I is determined by the factorization. They are unique, and they are called singular value of the matrix A. So this is why we call this calculation as singular value decomposition. Okay, so the factorization U sigma V transpose is called the singular value decomposition, or SVD in short. Okay, so this is the first definition notation. Okay, the notation of SVD, and we will show that the rank of A equals the numbers of the non-zero singular values. So go back to here. From sigma 1 to sigma n, sum of them would be 0. Okay? Sum of them would be 0 because we only want them to satisfy sigma 1 larger or equal to sigma 2 and so on, right? So sum of them will be zeros. And the numbers of non-zero singular value is actually the rank. Okay, is the rank. And the magnitude of the non-zero singular values provide a measure of how close the matrix A is to a matrix of lower rank. So this reflects the motivation of the beginning of this session, because we want to measure how close a matrix A to a matrix of lower rank. And we can see the non-zero singular, the magnitude of the non-zero singular values provide a measure of how close it is. OK， 好，所以这边我们提到说，非零的 singular value 其实就是 A 的 rank。OK， 这是第一个。第二个，如同我们一开始所说的，我们的动机是什么？我们想要去评判这个矩阵 A， 它在实际的功能性、实际的功能上面，它到底它的这个它应该是跟哪一个这个 rank lower rank 的矩阵在本质上是比较接近的。OK， 就好像说我们 singular value 可能一直从 sigma y 一直到 sigma n， 说不定到 sigma n 这个值已经很小很小很小了，好，已经非常小了。那其实这样子的数值很小的 singular value， 其实它可以被忽略不计，它代表的不是重要的，能够代表这个矩阵本质的一个数值，好，所以我们会去看这些即使它是 non-zero， 这些 non-zero 的 singular value 的数值，好，小到什么程度，以及到什么这个排名啊 ，sigma 1一直到 sigma n， 因为由大排到小嘛，这个排名大概是要排到多少，我的数值才够大？好，那所以等一下呢，我们会来讲这样子的东西。好 ，So let's introduce the theorem 6.5.1. This is called the SVD theorem. Okay, so if A is an n by n matrix, then A has a singular value decomposition. So this is quite simple. So for any n by n matrix, we can do singular value decomposition. Okay, now let's start the proof. And basically, if you check the textbook, you will see the proof is very long. So when we go through the proof of this theory, we can realize many properties of SVD. So let's start the proof. It's a very long proof. We use several slides to introduce the proof. Okay, so given a matrix A, n by n matrix, then we know A transpose A is a symmetric n by n matrix. right? This is simple because A transpose is n by m, and A matrix A is n by n, so the product of A transpose A is a symmetric n by n matrix. Okay, and according to the property of eigenvalues, a symmetric matrix, the eigenvalues of a symmetric matrix are all real number. Okay, and according to section 6.3, the matrix A transpose A has an orthogonal diagonalizing matrix V to diagonalize A transpose A. Right? We can find the diagonalizing matrix V such that the V transpose A transpose A V is equal to a diagonal matrix. Okay, this is from section 6.3, diagonalization. Right? Okay, and then we also know the property that a symmetric matrix, the eigenvalues of the symmetric matrix not only all real, but also non-negative. So the eigenvalues must all be non-negative. Okay, so you can check all these properties in previous sessions. Okay, so if you cannot remember these properties, please check again. And in the proof of theory 6.5.1, we use a lot of properties about diagonalization and eigenvalues. Okay, so all the eigenvalues are real and non-negative. Okay, so that lambda be an eigenvalue of A transpose A, and x be an eigenvector belonging to lambda. Let's say A transpose AX is equal to lambda x. Okay? Now, if we calculate the norm, the square of the norm of AX, then how can we calculate this? This is AX transpose times AX, right? Which is equal to X transpose AX. And now we know A transpose AX is equal to lambda x. So we can rewrite it like X transpose lambda x, which is equal to lambda X transpose x. And it's equal to lambda times the square of the norm of x. Right? So, what is lambda? Lambda is equal to the square of the norm of AX divided by the square of the norm of x, which is larger or equal to 0. Okay? So this is the eigenvalue of A transpose A. And now, that the columns of V, what is V? V is the diagonalizing matrix V that can do this. Okay? So, that the columns of V be ordered such that the corresponding eigenvalues satisfy lambda 1 larger or equal to lambda 2 larger or equal to lambda n larger or equal to 0. So remember that from section 6.3, how can we find this diagonalizing matrix? We just collect the eigenvectors of the matrix A transpose A. Remember that? We just collect the eigenvector of this matrix, and then we can form the diagonalizing matrix V. And here, we try to order we try to order the position of the eigenvectors such that the first eigenvector or the first column vector of V is the eigenvector corresponding to lambda 1. The second eigenvector is corresponding to the second largest eigenvalue lambda 2 and so on. So we intentionally order the eigenvectors in this way. Okay? And we define the singular value as the square root of lambda. So actually, sigma j is equal to square root of lambda j. Okay, so we define this singular value, and because the square root of lambda j would be positive or negative, and we only take the positive number. So now, let R denote the rank of the matrix A. So if the matrix A's rank is R, then the rank of A transpose A will also have the rank R. It's a m by m matrix. It's an m by m matrix. Okay. So since A transpose A is symmetric, its rank equals the numbers of non-zero eigenvalues. Okay, so this is another property you need to check again. Okay, for a symmetric matrix, its rank is equal to the numbers of non-zero eigenvalues. Okay, so this is why I say this session is a little bit complicated because it links many properties we described before. Okay, so you need to review again and again. Okay. So its rank equals to the numbers of the non-zero eigenvalues. So now, because the rank is R, that means lambda 1 is larger or equal to lambda 2 and to lambda R, which is larger than 0. And starting from lambda R plus 1 to lambda n, they will be all 0. So the last n minus R eigenvalues are zeros. Similarly, because sigma 1 is the square root of lambda 1, so from sigma 1 to sigma R, they are larger than 0. And the last n minus R singular values would be all 0. Okay, so now with that, V1, the capital V1 is equal to V1, V2 to VR. That means the first R eigenvector, where R is the rank of the matrix. And the matrix V2 accumulate the last n minus R eigenvectors. Okay? And with that, sigma 1, this matrix sigma 1, as a diagonal matrix, which is a R by R diagonal matrix. And its diagonal entries are the non-zero singular value sigma 1 to sigma R. So we define the matrix V1, V2, and sigma 1. Okay, and actually, the original n by n matrix sigma is given by this. This is an n by n matrix where sigma 1 is R by R, and this is R by n minus R. This is n minus R by R, and this is n minus R, n minus R submatrix, right? Okay, So now, let's consider the column vectors of V2. What is this? This is the last n minus r eigenvector. They are eigenvectors of A transpose A belonging to 0 eigenvalue, right? Because the first r eigenvalue are larger than 0. The last n minus r eigenvalues are equal to 0. Okay? So, the column vectors of the last n minus r eigenvectors are satisfy this following property. A transpose A times Vj is equal to 0 times Vj, because Vj is the eigenvector of A transpose A. So we can write down like this. And because the corresponding eigenvalue lambda is 0, so we can write down A transpose A Vj is equal to 0 Vj, which is 0 vector. So now, for j from r plus 1 to n, so now we know A transpose A Vj is equal to 0 vector. Okay? So what does that mean? That means the V1 Vr plus 1 to Vn form an orthonormal basis for the null space of A transpose A. So consider this equation. We can see that Vj are actually in the null space of A transpose A, right? And actually, this n minus r eigenvector form a basis for the null space of A transpose A. And we can further say it forms an orthonormal basis for the null space of A transpose A. Okay? Now, the null space of A transpose A, we can also say this space is equal to the null space of A. Okay, so this again is another property we can derive from the content we mentioned before. Okay, so the column vectors of V2 form an orthonormal basis for the null space of A, so that we can write down A times V2 is equal to 0 matrix. So we can write down like this. Okay? And now, since the matrix V is an orthogonal matrix, so this is the definition of the matrix V. Because it's a orthogonal matrix, that means V times V transpose is equal to identity matrix. Right? So now, identity matrix is equal to V times V transpose. And if we separate the matrix V into V1 and V2, what is V1? Remember that? V1 is the first R eigenvectors. V2 is the last n minus R eigenvectors. So if we separate V1 and V2, and then the identity matrix is equal to V1 V1 transpose plus V2 V2 transpose. Okay, so given the matrix A is equal to A times the identity matrix, which is equal to AV V1 transpose plus AV2 V2 transpose. Okay, and because AV2 is equal to the 0 matrix, so we can rewrite it like this, and we can remove this part, so that the final result becomes A V1 V1 transpose. So the matrix A is equal to A V1 V1 transpose. So finally, based on all these properties, we finally will introduce how to calculate U, sigma, and V. So now we have already known V is actually the eigenvectors of A transpose A, right? The matrix V is actually the collection of eigenvectors of A transpose A. And the sigma is actually the singular value, the collection of singular value at the diagonal entries. Okay, and remember that both V and the sigma can be separated into several parts, including the first R eigenvectors or the first R singular values. Right. So now we have already known how to calculate sigma and V, but how to calculate U? Okay, and because A is equal to U sigma V transpose, therefore AV is equal to U sigma, right? Because we can post multiply V at both sides, right? It becomes AV equals to U sigma V transpose V, which is equal to U sigma, right? So if we expand AV, it becomes A times V1 V2 to VR, and then VR plus 1 to Vn, which is equal to U1 U sigma, where U is an m by m orthogonal matrix, m by m orthogonal matrix. So U1 U2 to Un times sigma. Okay, so if we multiply them together, we will get sigma 1 U1 to sigma R UR. So we have first R values, non-zero values. However, starting from the R plus 1 to N, it would become 0. Okay, so we get this. So finally we know AVJ is equal to sigma J UJ, where when the J is from 1 to R. Really? Let me check our textbook. I think it's from, let me check. Oh, sorry. We cannot write down 0 here. We cannot write this. This should be correct. Okay? Yeah, because for the first R eigenvectors, the AVJ is equal to sigma J UJ. Okay, as we can see here. Here, the first R values would not be 0. Okay, so yeah, so AVJ is equal to sigma J UJ. Okay, and now if we define UJ equals to AVJ divided by sigma J, where J is 1 to R, and we define the matrix U1 equals to U1 U2 to UR, and then finally we can get AV1 is equal to this AV1 to AVR, which is equal to sigma 1 U1 to sigma R UR, which is equal to U1 to UR times the diagonal matrix sigma 1 to sigma R. So which is the U1 times sigma 1. U1 times sigma 1. Okay? So the column vectors of U1 forms an orthonormal set. Okay, we can verify this. Why? Because if you try to calculate the inner product between Ui and Uj, Ui is equal to AVI transpose divided AVI divided by sigma I. So because now we have a transpose, so it becomes VI transpose times A transpose divided by sigma I times AVJ divided by sigma J. So we can rewrite it like this, right? And because Vj is the J's eigenvector of A transpose A, so this becomes lambda JVJ, right? So we take the lambda J out, and because lambda J is equal to sigma J square, so it becomes this, and it becomes this. And we divided 1 sigma J, so finally we got sigma J divided by sigma I, and VI transpose Vj. And this value is equal to delta Ij, which is, this value is equal to 1 if I is equal to J, which is equal to 0 if I is not equal to J, right? We can verify this. So this is the criteria of orthonormal set. So the column vectors of U1 forms an orthonormal set. Okay. Now, since Uj is equal to AVJ divided by sigma J for each Uj, because we can write down this equation, so each Uj is in the column space of A, right? Because AVJ is equal to sigma J Uj, so Uj should be in the column space of A. And the dimension of the column space is R, because the rank of the matrix A is R. So U1, U2 to UR form an orthonormal basis for the range of A, right? And then the vector space, the rank, the orthogonal complement of the range of A is equal to the null space of A transpose. Then the null space of A transpose has dimension M minus R. M minus R. And that UR plus 1 to UN be an orthonormal basis for the null space of A transpose. And then we define U2 as the last M minus R vector. Okay? And then we constitute the matrix U by U1 and U2. Okay. So from the theory 5.2.2 that U1, U2 to UN form an orthonormal basis for Rm. So you can check this again. And again, we can see that U is an orthogonal matrix. So finally, we need to show A is equal to U sigma B transpose, right? So now U can be divided into U1 and U2. Sigma is sigma 1, 0, 0, 0, and the V is V1 transpose and V2, right? So if we do the multiplication, we finally get U1 sigma 1 V1 transpose. Okay, and which is equal to here AV1 is actually equal to sigma 1 U1 here. So finally, this can be reduced into, this is equal to AV1 and then times a V1 transpose. And because V1 is an orthogonal matrix, this is equal to identity matrix, so the final result is equal to A. So finally, we prove that by this way, we can do singular value decomposition for the matrix A. Okay, so this is very complex, right? So let me recall this again. What is V? V is the collection of the eigenvectors of A transpose A. What is sigma? Sigma is the collection of singular value of the matrix A. No, the singular value of the matrix A transpose A. Sorry. What is U? U is the collection of AVJ divided by sigma J. Okay, and all of them, U sigma V, can be separated into smaller parts. For U1, the first R component are non-zero. Okay, for V, the first R eigenvectors are considered. Okay, and for sigma, only the left top part consists of non-zero singular value. Okay, so this is the way we construct the matrix to do singular value decomposition. OK， 好，这个部分相当的复杂。好，我们借由证明这个定理6.5.1来了解 SVD 的很多的特性。很快的再讲一次，对于任何一个 n×n 的矩阵，我们都可以对它做 SVD。好，那这整个推导过程呢，好，先从列出一大堆特性开始。首先，我们知道 A transpose A 是对称的 n×n 的矩阵，它们的 eigenvalue 都是实数，而且大于等于0。那对于一个对称矩阵，我们都可以找到一个矩阵 V 来对角化这个对称矩阵，而这个矩阵 V 是谁呢？根据我们在 section 6.3我们提过的，其实就是这个 A transpose A 这个矩阵，它的 eigenvector 把它聚集起来，我就可以形成矩阵 V。好，那现在不仅如此哈，我们在这边呢，我们还希望说这个矩阵 V 呀，我不仅是聚集 eigenvector 就好，我还想要按照一个顺序，这个顺序就是根据我的 eigenvalue 的大小，对应到第一大 eigenvalue 的 eigenvector 就要排在第一个位置，对应到第二大 eigenvalue 的 eigenvector 就要排在第二个位置，这样子来形成我的矩阵 V。好，而 singular value 就定义成 eigenvalue 的这个square root， 好，它的平方。好，那假设 R 是 A 的 rank， 那么事实上呢，代表说你这个矩阵 A transpose A 的 rank 也会是 R。好，那对于一个对称矩阵 n×n 的一个对称矩阵，它的 rank 如果是 R 的话，那么它只有前 R 大的 eigenvalue 是大于0的，后面 n 减 R 的 eigenvalue 都小于0，都等于0。好，那同样的 singular value 也是如此。好，那我们刚刚讲的这个大 V 啊，我们讲说它是聚集了这 n 个 eigenvector。好，那如果说呢，我们把前面 R 个 eigenvector 视作一堆叫做 V1， 后面 n 减 R 个视作 V2， 好，然后呢，它对应的 R 个非0的 singular value 聚在一起，形成这个对角矩阵。好，那我们有了这些元素，接下来我们又去推一些特性。我们知道说，其实啊 ，AV2 是会等于0， 零矩阵的。好，而且 A 呢根本其实就是 A 乘 V1 乘 V1 transpose。好，好啦，那所以呢，我们现在已经知道说 V 怎么求， sigma 怎么求，那 U 呢？U 呢又经过这边这样的一个推算，我们就定义说，好，这里的 U 呢要符合 AVJ 等于 sigma J UJ。好，那所以我们把 UJ 呢设定成 AVJ， 再除上 sigma J。好，那尤其是前面 R 个，真正有作用的都是前面 R 个啦。好，所以这里就推出说 AV1 会等于是 U1 sigma 1。再往外延伸，好，我们如果令大 U 等于是 U1 跟 U2， 其中 U2 是接着后面的 M 减 R 个这个 U 的话，那么其实U sigma V transpose， 其实这整个乘起来呢，就会等于是原本的 A。好，所以呢，我们就可以知道说 U 怎么求 ，sigma 怎么求 ，V 怎么求，这样。好，所以这一块呢，真的是你要好好的、慢慢的一行一行，我们可以发现，刚刚我讲的每一句话，可能都会牵涉到我们之前在讲到对讲话，再讲到 eigenvalue， 再讲到什么 column space、null space 等等特性。好，每一句都有可能会连接到这些特性。OK， 好 ，OK， 好，所以讲到这边有没有什么问题？